Afternoon, folks, and welcome into the Resene Construction Systems Central Barrier and Intertenancy Walling System Seminar today. We're really pleased to have with us Resene Construction Systems General Manager Mike Holds. Hello there, Mike.
How you going, Rob?
Now, I'll quickly run through a bio on Mike before we start. Mike has an extensive and broad knowledge across the industry, with a primary focus on external facade durability and thermal performance. Having started with Rock Coat Plaster business in 1990 through to today with Resene Construction Systems, Mike has sat on the board of the Claddings Institute of New Zealand for a number of years and was a committee member for the LBP external plastering class when LBPs were introduced to the industry. Mike is also an honorary member of the New Zealand Institute of Building Surveyors. So that's enough about Mike. We should have time for questions today, and again, we've had some come through ahead of time, which is excellent. So we'll be firing those to Mike first, but please do type in any questions that you have, and if we don't get a chance, as usual, to answer today, we'll come back to you directly after the webinar. Right, so Mike and I are about to turn our webcams off, and I will hand over to you, Mike, to get underway.
Thanks, Rob. Welcome, everyone, this afternoon. We decided to do a presentation around the central barrier intertenancy walling systems. Not so much about specific systems. Obviously, what we'll be showing you today is a specific system. However, it's more about understanding how these systems are tested and where they're tested, and some of the requirements under the New Zealand Building Code. Obviously, with the massive uptake with medium density housing, land constraints, the opportunity and the awareness around these systems is being greatly increased. So to be able to provide some sort of context around some of the rigorous testing that's actually undertaken to achieve an accurate solution on the building site is a nice bit of knowledge to have under your belt. So our central barrier system, I mean, there's numerous systems in the market. But for obvious reasons, what I'm going to be talking about today doesn't specifically relate exactly to other systems, because I can't show you other systems being tested for obvious reasons. So this is one way that we can show you how the systems are tested and some of the requirements they've met. So as a start point, so a central barrier intertenancy wall system is designed primarily to prevent fire and noise going from one tenancy to another. And the two factors when a system's being specified is around sound and fire. Now, I need to make a note now that I'm not going to be delving too much at all into passive fire. When I'm talking about passive fire, that's penetrations through a fire and acoustic barrier system. All right, so the system we're dealing with today is purely central barrier in between tenancies. So I'm not dealing with corridors, lift shafts, and the like. All right, because there is a register for passive fire penetrations through fire-rated and acoustic-rated walling systems, but we're not dealing with that today. Today we're purely dealing with acoustic and fire for central barrier. So the key requirements for a central barrier walling system: they must be sound rated above 55 STC. They must be fire rated to a minimum of 30 and to a maximum of 120 minutes. And that depends on the requirements for that's been specified by the fire engineer for the specific project. And they equally must maintain structural integrity. So when I say structural integrity, so for the fire cell that's on fire, for example, that side of the fire cell needs to separate without affecting the non-fire side. All right, so I'll show you when we go through the fire testing, you'll understand how intense that is and how we actually achieve that. There is a number of ways that it can be done. I put this guy in here because if you've got bad acoustics and you failed a field test, or you haven't had a field test, you don't want to be going to bed like this guy here. And I trust if we get all this right in this space, then this won't be the situation. So in terms of acoustics, so the New Zealand Building Code Clause G6 deals with airborne and impact sound, and it sets the minimum sound requirements for intertenancy walls and floors of connected dwellings. I won't touch too much around the floors or the what we call the IIC. It's just purely around the walling at this stage. I do talk a little bit about impact sound and the difference between, for example here, airborne sound. So that's the STC. You'll commonly see STC being referenced, and that's the sound transmission class. So that's noise originating in the ear, such as voices, music, appliance noise, etc. And the idea with our central barrier systems is that noise at the frequencies that we test to achieve STC 55 don't transmit through. Some of the stuff you'll hear or see is, in terms of this airborne noise, is if you have a neighbour that loves drum and bass at full noise at 2 in the morning, a central barrier acoustic solution may not be the solution for that particular tenant next door, because it's very difficult to, this is just the STC 55 is very much the broad scope STC rating for noise in a general sense. It doesn't deal with extremes, all right? The impact sound of the IIC is the impact insulation class. And that's noise originating directly on the structure by blows or vibration, such as footsteps, moving furniture, knocking plumbing, HVAC, a number of other things. And it's one of the hardest ones to achieve, particularly where I think there are systems out there with batten and cradle systems where they do complete separation to get the best results around impact sound, because it's quite challenging with impact sound when you're carpet and underlay is generally not a problem, but when you start putting tiles on direct on surfaces and laminate timber floors, those noises transfer, and it's very difficult to isolate those unless you have a complete separation, like something like a batten and cradle system. So acoustic performance. So we deal with for the walling systems, the activities of other residents, such as loud conversations, televisions, loud music, and I mentioned before just about particularly around the bass, and equally it goes to the very high frequencies as well. So not just your drum and bass, but if you've got a neighbour that loves violin concertos at full noise at 2 in the morning, that you will tend to have some acoustic loss around that space. So we deal with plumbing systems, doors banging, appliance noise, washing machines, etc. And on the flooring side of things, they start to deal with your heating, air conditioning, anything going through flooring members. I mentioned earlier we don't really talk about corridors and lift shafts, but that is part of the IIC, vertical drainage pipes, external pedestrian and vehicle traffic, foot noise from the floor above is probably the dominant one, and adjacent walkways to stairwells. So STC, sound transmission class. So it's a single number system for quantifying the transmission loss through a building element. I.e. you'll see a number and so it'll be an STC and it'll be rated to a 64. So STC is based, as I said, upon typical speech and domestic noises, and is most applicable to these locations. STC of a building element is measured in approved laboratories, and the system that we're talking about and we'll be showing you the testing was tested at Auckland University in the Acoustics lab. And it's one of the more interesting venues I've been to in terms of testing and understanding how sound travels and the connection points and what can contribute to acoustic loss through a wall. And I was recently talking with Jan Schmidt, who's the head laboratory engineer, and we are going to be trying to get a group of individuals up there to have a look through that lab to understand how this testing is done in the first instance. There's another number you'll see around the acoustics, and that's you'll see an RW. Now that's a weighted sound reduction index, and that is probably the number that acoustic engineers look at as a safety. All right. So what it does, it's a rating of sound insulation performance of a specific element, and it's measured in the lab, and it's commonly used by manufacturers to describe the sound, installation performance, building elements such as plasterboard and concrete. So we can separate certain components out. So for example, if we have a client that wants to put, for example, 16 mil plasterboard on, they want to change the insulation, we can do that. All right, and then the weighted just gives you a bit of a safety factor. All right, so you don't have to go into your full scale tests. Flanking transmission is probably one of the critical ones. And now that is where we connect through elements at the end of a intertenancy wall, at the end of where the jib connects to an adjacent wall, and where it travels up into the ceiling spaces and things like that. All right, so those areas are specific and very important to the acoustic performance. Majority of walls you won't, unless you've drilled holes through the wrong places and got too many power outlets and the like, you generally won't have too many issues in the middle of a wall. They're normally around the perimeter of the wall. All right. The other one, and it's probably the scariest test after you've, because one thing is to build these solutions in the lab, is the field test. Now, the building code allows, it's a 5-point leeway. So for example, if you have an STC 55 under the building code and you achieve that in testing, when they come and do a site on a field test, they have a reduction, a 5-point leeway to take into account just the general on-site issues, like I mentioned, as flanking and the build quality and the like. So that did a little bit of redundancy around that when they do a field test, because it could be through windows on adjacent walls where there's a bit of noise coming through, a window might be open, things like that. So this is inside the Auckland University acoustic chamber, and the this section here, this is where we'll build a wall. So this building here, this is the sending chamber, and this is the receiving chamber. Now, these walls in here, from memory, are around about 900mm thick solid concrete. So there's no external noise coming into this site. You walk in here and it's quite an eerie space because it's like a big echo chamber. All the walls and ceilings are on different angles. This speaker thumps out noise at a certain frequency, and this rotates to share that noise around the space and bounces at different angles to ensure that the entire wall surface that we've filled into the space here has no acoustic leakage. And then here, this is where the receiving microphone is to actually pick up any noise that comes through from the space. I did touch a little bit on just the flooring. This section you can see on the bottom right of the screen, the white section of flooring. This is a big solid slab of concrete that is on hydraulics, and that lowers and raises depending on the floor system that's built into this chamber. And exactly the same process essentially occurs. They do change this a little bit in terms of when they're doing an impact test, they have what they call a hammer test, and they put a little box on the finished flooring that you're testing, and they essentially tap, 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 and it transfers and it sees if it isolates that noise from below. All right, so what we're dealing with here, we're looking at this space here, and this is what we are going to be filling into. So the system, our system is a lightweight concrete walling system with a bracket with brackets, separation brackets from the structure. So we build this wall into that space so that's completely built live on site, and we essentially build the wall up as in accordance with the specifications. So you can see our panels in here, the brackets that are fixed through, and these are the brackets on the opposing side, because obviously we have there's two frames, and our wall sits in between. As a breakdown of the system, if we looked in the top of that wall, we have our framing that you just saw, this framing here, and on the other side you have the other framing for the other side of the tenancy. The brackets are fixed in through the panel and into the framing. This gap here is generally in most situations with 20 mil. We do allow the system to go out to a 40 mil bracket and 40 mil cavity. or air gap, and that is dependent on the services that are required on each tenancy side. All right. Part of this particular system, this bracket's an aluminium bracket, which I'll allude to a little bit later on, the importance of it being aluminium, but there's also silicon dampeners connected to it. So the silicon dampeners are connected against the framing, into the bracket, and also against the wall. So they help with dampening any vibration or noise vibration across the walling system. We put in insulation into the wall space as you would normally do, and that can change. That's essentially can be changed to what other type of insulation you want to put in that wall, and that's where we can do some. There are ratings where the acoustic engineers can change insulation requirements and give opinions around that type of insulation into the walling. In this instance here, we obviously used a standard pink bed insulation. Once the insulation is installed, we then go around and we install a layer of, in our test, we did 10 mil plasterboard, and part of why we did a 10 mil plasterboard as an initial requirement was that is the most common plasterboard applied to internal linings. We wanted to look at this solution, so instead of having different types of plasterboard installed on projects, we went with the most common to try and avoid any crossovers with different types of thicknesses and different deliveries and things like that to the project. So we went with the standard 10 mil. We did the first test. You can just see it here. We've got the first layer of plasterboard here and the acoustic sealant around the perimeter. We also we did that, so then we acoustic tested that, and then we went through and we put a second layer over it as well, because what we were trying to see if we can get improvements around our acoustic performance at different layers of plasterboard linings. So with our first test we did was a single layer plasterboard, and that achieved an STC of 64. All right, so the standard 10 mil plasterboard. When we applied that second layer, we jumped up to 67 STC. So that gives us tested results just on the 10 mil. We do have our numbers there from our acoustic engineers on 13 mil and the like. But what we really, like I said, what we're really trying to do is trying to have that most common material supply onto sites without any crossover, and then equally understanding what sort of performance we could get. So as I noted earlier, the building code requirement was STC 55 as a bare minimum. We sit there with an STC of 64, which is well above the building code. There is also an RW, or a weighted acoustic rating there, of 62. So we got some reasonably good redundancy there within the system. The next category around central barrier into tenancy is fire, and this is probably the most impressive test that you actually get to see, and the intensity of the walling system goes through. And this is one of the, not the most common thing that occurs in a building, obviously, but certainly one of the most important in terms of life. So under New Zealand Building Code clauses C1 to C6, so there's protection from fire, so give the minimum fire safety requirements. So the building code objectives to safeguard people from an unacceptable risk of injury or illness caused by fire, protect other property from damage caused by fire, and to facilitate firefighting and rescue operations. So firefighters, they will go to a property, they will know whether something's potentially going to collapse or not, if they can go into the adjacent property after the timeline of the fire. There's a whole number of things that protect people around the space. So when we do this testing, it's it's our most intensive testing and probably the scariest from our side in terms of what can potentially go wrong. We're not going to die from noise, but if there's something happening around the fire space, then that's what we're most aware of. So the key thing that you'll see when you're looking at Intertenancy wall is what they call the FRR, or the fire resistance rating. So that's the ability of a building element to withstand fire under test conditions for a period of time. And there's three key criteria. So you'll normally see, for example, 30-30-30 or 120-120-120, as we'll be showing you, and they're in an order of appearance. So for stability, is the first period of timeline here. That's the ability of the element to carry an applied load. So if it's single story, two story, the roof, that's the ability of that structure to carry that load. And from recollection, that load that was applied was 4.5 kilonewtons of load. The integrity is the ability to prevent fire to jump from obviously the non-fire side, so the fire side to the non-fire side, or the creation of gaps to allow the passage of gases to enter into the non-fire space. And it's the insulation is the final number we see here, and that's the ability to limit the temperature rise on the non-fire side. All right, so that's not talking about the pink bats or the insulation of the wall. This is about the central barrier, or our Integra lightweight concrete in our case, to limit that issue of temperature rise when there's a fire on the other side. So we do all that testing at brands, and this is essentially we go into brands and we build a wall as we did with the acoustic lab. It's a slightly bigger configuration, and our brackets are installed as they would be in accordance with our specifications. Panels installed. I didn't mention earlier, but we also run we bond our panel joints with a mortar, just to connect the panels and to provide some stability, but also to eliminate any gaps between the panels when getting tested, and also for acoustic and thermal performance as well. So the brackets are installed, the wall's built. This face will have the plasterboard applied to it. We did something slightly different in this test, and I'll show you shortly. When we talk about redundancy, we love redundancy in this type of situation, and we also put polyester insulation in the walls rather than fiberglass insulation in this situation, because we want to get a worst case scenario. We want to see if the polyester insulation will contribute or be more hazardous in our situation. We know fiberglass performs very well under fire load versus something like polyester. So I mentioned earlier, and I showed you this graphic when we were talking about acoustics, and we had our silicon dampeners around the actual aluminium bracket. The key one was around the aluminium. Now, one of the key things with aluminium is that it has a melt point of 660 odd degrees Celsius, which is some 400 degrees, 330 degrees lower than what this furnace temperature is. The idea in them being aluminium is that they melt away. So if this is our fire side over here, there's a fire in here, these melt at a lower than what the expected temperature would be on a full fire, so that this structure, these components fall away to the fire side without compromising the integrity of the central barrier wall and the structure on the other side, all right, to allow people to vacate, etc., etc. So they're an important component of what we do. In other systems, they have rails at the tops of the walls and onto the floor, and they don't have connection points to provide that type of surety around that space. So they are an important component for us. When we did our test, and I mentioned redundancy before, so we've built our wall, and from the previous image, you saw the framing that you can't see here at the moment. On the other side of that framed wall, we decided not to do framing on this side. We thought we would eliminate the timber and the plasterboard and the polyester polyester insulation on this side, and we just wanted to put the central barrier straight into the furnace and see how that performed. And from talking with the fire engineers and during the test, by not having the framing and the plasterboard and the insulation on the inside of the furnace, we probably gave ourselves probably another 15 to maybe 20 minutes on top of our testing time. That's all that framing and that plasterboard would deal with under the temperature that we expose it to. So it was probably a more extreme test. And once again, that's just around redundancy and surety of the system performance. So as you can see, we've still got our screw fixings that are fixing the panels to the brackets, or the mortar joints that we just apply mortar onto the panels, and obviously our intumescent sealant and foam around the perimeter. So over here, this big red box, that's our furnace. So on the other side that I showed you the framing before, we put plasterboard over that and do it as we would do on the non-fire side tenancy. The other thing that you can see here is all the thermocouples. So all these wires you see here, they're connected. I need to stress that these pipes do not go through the wall system. They are there for services that would run inside that cavity or inside the framing line. And we have thermocouples connecting to the fixing brackets on the inside of the wall, against the jib board. And what these thermocouples are doing, they're measuring temperature across the entire surface, so that there's a maximum. I mean, technically under the fire, the wall will be warm enough. You know, you won't be able to hold your hand against it. You'll know there's a fire on the other side of it. But the idea of the thermocouples is trying to find these hot spots and areas that would raise concern under a full-scale fire. To give you an idea, when we're looking at these fire tests and into this furnace, that's what 1,000 degrees looks like, and that's the temperature that exposed wall here was getting exposed to inside the furnace. So it's not a nice place to be. And all those thermocouples that I was just talking about, they do a data log, and this was at 91 minutes. And we talk about the temperature across these thermocouples. So there or thereabouts around that 1,000 degrees. All right. And then each of the thermocouples are logged in temperature. And we have a couple of spots here where maybe something's touching a bracket or something along those lines, but it's very isolated. The key number we have a look at is the average. So the average temperature rise at these temperatures at 91 minutes was only 66 degrees. So you'd know it's hot on that wall, but that's pretty much it. You know, you won't be seeing fire bounce through and things like that, or smoke and things like that come through to the non-fire side. Even though when we built this wall into the test rig and the test booth, even after 7 days of it just sitting there, basically preparing to get put into the furnace, you can still see the heat and steam pushing moisture and vapor out of the building componentry, be it the timber, be it the mortar, be it the panel, those sorts of things. So there's an intense amount of pressure inside this room and the space here, and obviously all the thermocouples on the outside here. This is the end of the test, and so at 125 minutes, we had no failure. Now, bearing in mind that we didn't have framing and plasterboard and insulation inside directly into the fire side, on the fire engineers saying you could grab yourself another 15 minutes. So there's quite a bit of redundancy over our 120 rating that we've actually achieved with the system. So the test that we did, that was your lining, your framing, insulation, and our panel. All right, so this is what we saw with the thermocouples. This is the structural framing. This is the Integra lightweight concrete, and then we had furnace, so we didn't have this componentry in here. All right, and our result was a full 120, 120, 120. So that, in a nutshell, is the system, and it's important to, I think, understand and see that testing, which is which you don't always get to see for obvious reasons, as I've alluded to earlier. So without further ado, I will take some questions.
Thanks very much, Mike. Who knew that central barrier intertenancy walling systems would be so interesting? So a lot of good info in there. I don't know if you want to flick your webcam back on again, and so we can see your mugshot. There we go. Excellent. We have had a couple of questions come in while you're presenting from the field, and as I mentioned, we've got a few that have come in previously. I've actually jotted a couple down myself that I'm keen to ask first, and as usual, because I'm in control, I get to do that. So I'm interested to know why is the test only to a maximum fire rating of 2 hours?
We only, I mean, part of the when I talk about redundancy, we could have, as you can see from the testing, we could test less, but from a performance, we don't necessarily want to be in the space of just doing a minimum. Yeah, I mean, we could do 30 minutes, 60 minutes, 90 minutes, 120 minutes, but we just wanted just an all-encapsulated system. So, for example, the solution covers everything. So that was sort of one of our prime goals, and the same work for the acoustics to try and get the highest level rating in acoustics we could, as a standard specification. All right, so I don't give you too much more room to move around there. So it's confidence in a system, to say, well, if you don't need 120, but you can still achieve it at a cost efficient point, why not just do 2 hours to provide that surety?
Very good. Another one from me is just on your paneling system. I know you're kind of trying to give good generic industry info there, but are the panels that you're talking about, is there an issue around weather? Do they get affected by moisture or if they're exposed?
No. So in I suppose it's one of the tricks, and it's sort of like a flooring system and a walling system. Is generally these walling systems are always done generally before the floor, the roofs are installed. So it's a lightweight concrete. It's inert once it's installed, and it's not affected by UV or rain. It'll certainly absorb some moisture, but it doesn't affect its the componentry whatsoever. So there's no protection, other alternate protection required while the rest of the structure is being built, the other walls, and obviously getting the roof on. So
excellent. Now I'll get into a couple of these questions that have come in while you're presenting. One from Stephanie Gardner. Thanks, Stephanie. You were talking about the framing requirements. Do you need to alternate the framing from one side to another?
No, not generally. So what we'll do is we alternate. So that's around our fixing point. So whatever the requirements are under 3604 for each tenancy, we change our bracket locations. We'll fix on one stud, but then we won't fix a bracket directly opposing that. We will go to the adjacent stud. As long as we have two brackets fixing each panel, and each panel is 2.2 meters long. As long as we have two fixing points on alternate studs, they can't be adjacent to each other, those brackets, then we're fine.
Cool. One from Martin. How much seismic movement can your system take and maintain to maintain its fire and acoustic rating?
So we haven't. I haven't done anything around the seismic. We've certainly tested under 3604 under those loads that are capable for that. But it is something that we are investigating further, and that it relates a little bit more for us around how we move into our corridor space and lift shaft space and things like that. But that's some future testing that we're going through. But I will come back, and if you can send me that email, I can send through some correspondence around that.
Yeah, no, very good. We'll record all the questions as we go, so we'll fire that through. One from Rowan Murray. Thanks, Rowan. What testing is there on the aluminium brackets and their failure mode? This wasn't included in the test at brands with framing and lining on only one side. So I might be reading that incorrectly. How can we be confident that the frame and lining on the fire side will not be damaged, will not damage the Integra panel when the brackets melt?
So when we were speaking with our fire engineers, we based so in terms of the aluminium brackets, their melt point and what that furnace temperature is, and obviously they would fall away. So that wasn't part of that, part of obviously the testing that I showed you. However, I will send something through to that person that's asked that question in regards to that from our fire engineers. I should also add that we can, if they look on our website under construction systems, they will actually see we're pretty transparent about every test and every report that we have around this space. So we include the full test reports. We don't just give little snippets. You actually can just grab the entire test reports that are available on our website. All right. And if you go and click on the system, Intertenancy system, click on the specifications and scroll down, there's a tab there with useful documents, and there are screeds of useful documents sitting within the and all the testing and stuff that we actually achieved that may assist in that space as well.
Mm-hmm. One from David Marsden is probably in a similar area. Is there a separation product to the angle required to steel framing as well as timber?
In terms of connecting against steel framing, no. So our bracket system is identical to what we will use for timber framing. We don't, if I'm getting his question correct, we don't change our bracket system or connection point to steel framing. That's what we'll do with timber framing.
Next from Patrice, without panel joint mortar, just a standard plaster stopping system, is the fire integrity of the wall compromised? Can
you repeat that again, please, Rob?
Without the panel joint mortar, just a standard plaster stopping is, I'm assuming that is with just standard plaster stopping, is the fire integrity of the wall compromised?
Yeah, I mean, when we put the panel system requires that mortar to be applied between the panel joints, and each panel sits on that bed of mortar as well. So I'm just trying to think. So if you can't just rely on obviously the plasterboard to achieve that fire rating. All the fire load is put onto the panel. So you can't. I mean, if you did a plasterboard solution for the fire rating, then that's a different story. But in terms of what we were talking about and dealing with was almost the plasterboard and the framing on that fire side doesn't affect the integrity of our fire rated walling system.
Very good. One from Mahatvani. I hope I've pronounced that right. Apologies if I haven't. Does the board system run through the interfloor joist spaces?
Yes, it does.
That's a nice easy one. One from Dave McLeod. The system, so is a system for terraced homes only and not apartments?
We generally deal with the medium density. I mean, this particular system, we're up to 12 and a half meters as a maximum height for this. So we're generally speaking about sort of medium density housing. We're not talking full height apartment walk-ups and things like that, because that's corridor space that's more in relation to accuracy of passive fire connections and penetrations through these acoustic and fire rated walling systems that we haven't completed testing on yet. So our dominant space is very much in terraced housing and the medium density housing space.
Another one, is it more common to use a 40 mil gap for trades instead of the 20 mil cavity on site?
The most common currently is 20 mil.
Very good. One from Julian Wilson. What kind of field testing have you done?
I think there's a couple of projects. I haven't got the actual field test reports back on those projects, but we certainly, I mean, numerous projects getting field tested currently, and I mean, it seems to be getting more and more common around the space, obviously, with the uptake of the volume of medium density housing, but from my accounts and feedback, they've all been very positive and achieved the required field test requirements.
Another one from John Berridge. What about concrete intertenancy walls, either precast panels or infilled concrete blocks? Does the MPA make a difference with or without strap and lining?
In terms of the MPA and the strength of the concrete within that wall, I mean, that's whatever gets specified by the engineer or the fire engineer, and it's not something that I I really couldn't comment too much further on. That's a structural load bearing acoustic and fire rated walling system. So you'd have to talk with the idea would be you talk with your fire engineer around that space, and equally those at be it Firth or other businesses that deal with that type of solution.
Very good. Now, I think you've broken the record here with questions coming in, Mike, because they're flooding in as we go. So I'll ask one or two more, and then I think what we'll do is close off for the day, and we'll be corresponding back to everyone directly to answer the questions. But thanks to all that are asking them. It's as I say, I think Mike's broken the record here today. So we'll just
it's either a good sign or a bad sign, one of the two.
Yeah, that's right. So this is an interesting one, relatively simple question, but is a specialist installer required to install the panels?
No, so we have, generally a lot of builders are installing the system due to the speed and ease of it, but they're also requesting contractors, generally LVP contractors, to come in and install the system. So we like to go down that space in terms of LVP. It's not considered as restricted building space because it's not structural, but around we prefer it to be an LVP, has a good understanding of the constructed space and how their system's put together.
Very good. One from Sam McCabe. Are you looking at thinner panels to reduce costs and fit more standard to a more standard 30-minute rating, or does the acoustic level not allow this?
We have some limitations, and obviously in the thickness of the panel. I mean, 50mm would be the minimum thickness we would want to look at for this particular product, and part of that reasoning is, I mean, the total overall performance that we get with 50mm is superb. To go to something half its thickness, we couldn't do like 25mm. You're saving yourself, like I say, 12mm either side. And a potential reduction in its performance. Like I said at the very beginning, we really want to have a high performing intertenancy walling system that is that exceeds what the requirements are under the code. And it's also a factor around obviously the product that we have is currently at 50mm. There's no product of its like at 25mm outside of your plasterboard solutions for those central barrier walling systems.
Very good. As I mentioned, we have had a fair few quite technical questions come in, so thanks to all those that have fired them through. And Mike will get the chocolate fish for breaking our record with questions following the webinar. But we will come back to you all, and they're just reading through them. There are some really interesting questions. So this obviously is pretty topical and type of subject that Mike's covered today. So thanks very much, Mike. It's been very, very interesting. Very much appreciate your time. We will sign off now, and thanks to all the team that's tuned in and viewed today. As usual, there'll be a follow-up email from us, and it will have the contact details for Mike and the team at Resene Construction Systems, and also the link onto our website to watch this webinar again if you wish, and any other webinar that we've presented over the last 12 or 18 months. So thanks again for tuning in, and we will see you all next time. Bye for now.
Thank you very much. Cheers,